Hello everyone from Math 1340, Statistics. It's Professor Wenson here again with a video for you on your KnewtonAlta homework for section 3.3 titled Two Basic Rules of Probability. Now we have seen in earlier sections, earlier videos of mine that what it means for events to be mutually exclusive and to be independent. So those words will come back in this video, so hopefully you remember those. If not, go back and look at the section 3.2 video for those definitions. Alright, so I'm going in here to your 3.3 KnewtonAlta homework. And you can see there are 4 objectives in this one. And the first one is use the addition rule for probabilities. So first time I'm seeing this objective, I'm going to go to more instruction. Show you what that looks like. So they have an example to start right away. I'm not going to do that. I'll let you read that. Here we go. Remember a compound event or a combined event with the word or, and there was also ones with the word and. This is a rule that you should really get to know pretty well. And I'm going to go to a piece of paper as well. I'm going to write out this rule and also talk about, there's a shorter version of this for when the two events are mutually exclusive. And that's actually another objective, so when we get to that objective later, I think I might just skip the instruction. But let me show you this on paper. Okay, so here's what that rule is. For an event A or B, the probability of A or B, this event, is equivalent to the probability of one event, A, plus the probability of the other one, B, minus the probability, you don't want, if you just added these two, you'd be counting the outcomes that they have in common twice. So we need to take those away once, right? So I subtract the probability of the outcomes they have in common, A and B. Right? Now I'm putting number 1 next to this because you also have this, a second rule, which is the same rule but shorter. If A and B are mutually exclusive events or disjoint events. So hopefully you recall from last video, last section 3.2, when events are mutually exclusive, that means they have no outcomes in common. They can't happen at the same time. Meaning that this probability here, after the minus sign, would be 0. Right, so that disappears in this addition rule. So the probability of A or B occurring if A and B are mutually exclusive is simply the sum of the probabilities of the individual events. Right, just getting rid of this last part because that last part would just be 0. Right. So this is one objective in this assignment, and this other rule here is from another objective, right? I mentioned there are 4 objectives here. So I basically summed up 2 objectives on this one page. Alright, so they go through an example here. I'll just get to a problem. Alright, there's another one here. Great, and the addition rule, cool. Let's just get to a problem. So here there are 2 known issues with a certain model of a new car. The first issue, A, occurs with like faulty brakes or something, whatever. The first issue, A, occurs with a probability of 0.1. Right? The probability that A occurs in this model of car is 0.1, 10%. B is another known issue with the car. If it is known that either event occurs with probability of, the probability of A or B occurring is 93%, right? So this is the probability that one occurs or the other one occurs or both of them is 93%, 0.93. and that both events occur with probability of 0.07. The probability that they both happen on the same car is 7%. What would be the probability that issue B happens on a car of this new model, of this model? Right, so I'm going to write this out. So I'm just going to the rule right here. We have the probability of A or B occurring. Now that was given to us. We were told that the probability that issue A or issue B occurs on one of these cars is 93%. So there's a 93% chance that one or the other thing is going to happen, or both. Right. So I put 0.93 there equals. We were told also that the probability that issue A occurs for one of these cars is 10%, 0.1. Plus, now the probability that issue B occurs, we were not told. That's unknown. I can call it like X or something, or just leave it like this. This is the unknown. Alright, and I'm going to be doing a little algebra here, just solving for this in a minute. Then minus the probability that both issues occur at the same time in a car, one of these cars. And the probability of A and B was 7%, 0.07. Okay, and then I'm taking this and simply solving for the probability of B. Right, so to do that, just again some simple algebra. Just subtract 0.1 from both sides. Maybe I'll call it 0.10, so they're all at the same decimal point. And then I would add 0.07, right, because it's already negative, right, to get the P of B alone, the probability of B alone. And I add 0.07. And putting all that together, we get the following. Right? I'll just switch sides here. The probability of B would be equal to 0.93 minus 0.1 would be 0.83 plus 0.07 would be 0.90, 0.90 or just 0.9, 90%. Alright, so the probability of this issue B occurring in one of these vehicles is a 90% chance, right? 0.9. And it just says, now everything was given as a decimal, so I'm going to write mine as a decimal, 0.9, and enter. They didn't say to go to so many decimal places, so that's it. Right? And then again, they go through the same thing as I just did. All right, you take the formula, the addition rule, and solve for probability of B. Okay, so something very similar. If A and B are events, with the probability that A occurs is 0.5, probability that A or B occurs, one or the other or both, is 0.65. The probability that they both occur at the same time is 0.15. What's the probability of B? All right, so it's basically the same problem. All right, I'll show you again. So here's that addition rule. Right? The probability of A or B is the probability of A plus the probability of B minus the probability of A and B occurring. And we were given all but one of these things. Right? There are 4 probabilities here, and we were given 3 of them. We were given the probability of A was 0.5, so I replace that with probability of A. Plus the probability of B we're trying to find again. So I'll leave it as the probability of B minus the probability of A and B is 0.15. And then we were given this as well, the probability of A or B occurring 0.65. All right. So again, I would subtract 0.5, making this 0.15, and then add 0.15. The probability of B occurring would be 0.30 or just 0.3, 30%. It's really that simple, a simple arithmetic, simple algebra. So here, it doesn't say to go to so many decimal places, so I'll just enter 0.3. Great. All right, so this one is a little different, but still the same, using the same rule, right? If A and B are events, the probability that A occurs on its own is 90%. The probability that B occurs on its own is 30%. The probability that either A or B occur, or both, one or the other, or both, is 95%. Then if all those are true, what would be the probability that A and B happen at the same time? Right, A and B. So one more time, I'll show you the rule, and we'll just plug some numbers in. Right. So we were given this, right? The probability that A or B occurs is 95.95, right? Equals the probability that A occurs on its own is 90%, 0.9, plus the probability that B occurs is 0.3. And we're trying to figure out this, the probability that A and B occur at the same time. Alright, so these here together, 0.9 plus 0.3 is 1.2, or 1.20 if I want to take it to the same decimal place. Then I would subtract this, and we'd have negative 0.25 equals, and then this is still minus here, negative probability of A and B. And so just multiplying both sides by -1, I get the probability that A and B occur is 25%, 0.25. So that's what I'll enter. 0, and it doesn't say to go to any decimal places or anything like that, so just enter it as is, 0.25. Hopefully very, very easy for you. So if this is another one like that, I'll just do the instructor cheat. Yeah, this is exactly the same kind of problem. You just, in that rule, that addition rule, you have 4 probabilities stated. You're given 3 of them, and asked to solve for the one you don't know. So I'll just do the instructor cheat to move on here. I know you can't, and you actually have to do it. All right, so that's one objective. All right, the next one that pops up here, say use the addition rule for mutually exclusive events. Now, you could click on more instruction, but I've already shown you that rule, and I've already discussed it a little bit. That's this rule here. All right. So getting rid of this, if events A and B are mutually exclusive, right? That means they can't happen at the same time. Then this probability of A and B would be 0, and I'd get rid of it, right? And then you have this addition rule instead. All right. So if you know that 2 events, can't happen at the same time, you can use this much shorter version of the rule with only 3 probabilities instead of the 4. All right, so I'm not going to click on more instruction. I'm just going to do some problems then. So Randy wants to either ride share to work or drive his own car to work. You see that those are mutually exclusive, right? Because it's impossible for Randy to ride share and drive his own car in one trip, right? You can't share a ride and drive your own car at the same time. So, if the probability that Randy ride shares is 22%, and the probability that Randy drives his own car is 42%, what is the probability that Randy ride shares or drives his own car to work? All right, so I'll write this out with letters. All right, I'll show you. I know you can already probably tell what the answer is going to be. Let me go back to the paper here and show you if I wrote this out with letters. So we see that I'll say event A is Randy ride shares to work, and I'll say that event B is I'll just say he drives his own car. I'll just write own car. And we know that the probability of A and B happening at the same time is 0. Right? Remember, this is what it meant to say that A and B were mutually exclusive. Right? It's impossible for both of them to happen at the same time. So we're using this addition rule now instead. The probability of A or B, right? That's what they're asking for, right? They're asking for, what is the probability that Randy ride shares or drives his own car? So ride shares or drives his own car. That'd be equal to the probability of the ride sharing plus the probability of driving his own car minus 0. That minus the probability that they both happen, but again, they can't happen at the same time. So it's simply 0.22 plus 0.42, right? The two numbers that were given to us. So putting those together, 0.64. 64% chance that he ride shares or drives his own car. It's a simple addition. Okay. All right, so this is a different objective. Use the multiplication rule for independent event probabilities. All right, so I'll show you the more instruction on this one and also write some things on paper coming up. So here it is. Now, hopefully you remember this definition from section 3.2, right? The concept of events being independent came up in that section. Remember, two events, A and B, are said to be independent if the probability of one occurring does not affect the probability of the other occurring or happening. So, and this also came up in section 3.2. Here was one way you could show that two events were independent. Right. Events A and B are independent, then the probability of A and B happening at the same time will simply be the product of the probability of A and the probability of B. Right. So I'll write that up on some paper, and we'll refer back to it when we look at some problems. Right. So here's the multiplication rule. Now I'm actually going to write two of these. Right. Just like there are two addition rules, one when just there was that one general rule, and then the one rule when the events were mutually exclusive. First one here is if A and B are independent. Then you have the probability of A and B occurring at the same time. Right, this is so the addition rule started with or, right? A or B. The multiplication rules that you're going to see here start with and. The probability of A and B occurring at the same time. If these two events are independent, right, meaning that when one happens, the probability of the other one happening is not affected. You saw it in section 3.2. Please go back and look at 3.2 if you're unfamiliar with independence. Is simply equal to the product of the individual probabilities. The probability of A multiplied by the probability of B. Right. Now there is a second rule, okay, that involves conditional probability, and this is more general. More of a general rule. This applies when they're independent or dependent, but this one looks a lot nicer right here when they're independent events. But the probability of, and this is the fourth objective, like the third objective is this guy, the fourth objective is going to talk about this one. The probability of A and B occurring is equal to, I'll pick an event. Again, say A happens first. So it's the probability of A happening first multiplied by, and then a conditional probability. The probability that B happens given that A has already happened, right? Remember this notation for conditional probability. And do you see why when A and B are independent, you get this formula up here. All right, remember what it meant for two events to be independent. The probability of B given that A has happened would just be the probability that B has happened. A happening doesn't change the probability of B. So you see this here, the probability of B given A is just replaced with the probability of B. So that's why you get this formula for when the two events are independent. Right. And we'll come back to this one in the last objective. All right, so sticking with this formula, right? When we know two events are independent, the one happening has no effect on the other happening. Let's get to some problems. All right, so they run through an example here. I'll just go to a problem. All right. So first year nursing students are randomly assigned to classes in a nursing school. Let A be the event that they are assigned to an anatomy course, and B be the event that they are assigned to a psychology course. The probabilities of them being assigned to these courses are as follows. So the probability of the probability that a student's assigned to an anatomy course is 2/3. The probability that a student is assigned to a psychology course is 2/5. Now they're saying if A and B are independent events, right, meaning that if a person's put into an anatomy course, that has no effect as to whether or not they're put into a psychology course, and vice versa. If A and B are independent events, what would be the probability that a nursing student is assigned to both an anatomy course and psychology course? That's A and B. All right, so again, very simple. If you know the events A and B are independent, we're going to jump in here, and then the probability of A and B occurring, right? The probability of being in an anatomy course and a psychology course at the same time would be equal to the probability of being in that anatomy course 2/3 multiplied by being in the psychology course 2/5. This is 4/15. And it does say enter your answer as a fraction. So product of those 4/15. Very, very simple. And that's if we assume those are independent events. Okay. So another one on. No. Okay. Now we're back. Pay attention to the objective. This is that addition rule for mutually exclusive events. All right. So I'm back to this rule. Right here. Right, if A and B are mutually exclusive events, the addition rule. Right. So suppose A and B are mutually exclusive events, right? They cannot happen at the same time. And the probability of B is 48%. And the probability of A or B occurring, one or the other or both, well, not both because they're mutually exclusive, but the probability of one or the other occurring is 0.98. What would be the probability that A occurs? So hopefully you can see that that's 0.5. But I'll go here and we're going to this formula. We are given this. All right, this is 98%. We don't know the probability of A, so I'll leave it that way. And the probability that B occurs is 0.48. And all I would simply do is subtract this and get the probability that A occurs is 0.5 or 0.50, 50%. All right. Pardon me. So 0.5, right, 50%. Right. So back to that multiplication rule. Right, pay attention to the objective again for independent events. All right, so here, two psychologists are studying the IQs of a group of business professionals. So let A be the event that a professional's IQ is greater than 115, and the probability of that happening is 16%. Let B be the event that a professional's IQ is between 115 and 130, and the probability of B is 14%. The IQs of different professionals are independent, right? Looking at the IQ of one person, if one person has an IQ greater than 115, that has no effect on to whether or not the next person you talk to has an IQ of greater than 115. That or between 115 and 130 or whatever, right? One person's IQ and another person's IQ are independent of one another. So then what is the probability that two random professionals will be chosen and one of their IQs is greater than 115 and the other one is between 115 and 130? Right. So now we're here. Right, we're talking about the multiplication rule now. Right, we are talking this rule for independent events. Right here. So I said A was IQ greater than 115, B is IQ between 115 and 130, and they want the probability that two people selected, one of them has an IQ greater than 115, and the other one has an IQ between 115 and 130. The probability of A and B, and it said they were independent, right? So here it's simply going to be now 16%. That was the probability of A having an IQ greater than 115 times the probability of having an IQ between 115 and 130 was 14%, which is 0.16 times 0.14 or 16 over 100 times 14 over 100. And now 16 times 14 is I believe 224. All right. But then we move the decimal place to the left 4 places. So this is 0.0224, I'm pretty sure. All right, and if you'd like to double check, I'll double check myself here. I'm not that confident in my abilities. I know I should be, right? So let's click. That's from an earlier video. So 0.16 times 0.14. Yes, 0.0224, which is 2.24%. If I move the decimal place back to the right 2 places. So the probability that both these people, satisfy this, that one has an IQ greater than 115 and the other person has an IQ between 115 and 130, there's a 2.24% chance of that happening. Right. Now they said give your answer as a decimal rounded to 3 decimal places. Didn't say as a percentage, so this is a decimal. So going back, that was this. Now to 3 decimal places. So 0.00022, and then you'd round down because the next digit's a 4. So 0.022 is what I'm going to enter. 0.022. Always read how they want you to enter the answers because it is pretty strict. If you've gotten this far, you've probably noticed they're pretty strict on how they want you to enter answers. Because if I entered it as a percentage, it would have told me it was wrong and all that. All right. So please read and be careful. All right. So here's another one. Now this is again just a multiplication. Oh, this is the addition rule for mutually exclusive events. So I'd just be adding these. I think. Hold on, let me read it. At a certain school, Intro to Economics and Intro to Calculus meet at the same time. So it is impossible for a student to take both classes, right? So they're mutually exclusive classes. If the probability that a student takes Intro to Economics is 0.57, and the probability that a student takes Intro to Calculus is 0.17, what is the probability that a student takes Intro to Economics or Intro to Calculus? So I'm doing an or probability, meaning addition rule. And they're mutually exclusive, so that was just simply adding them, remember? 0.57 plus 0.17 would be 0.74, right? So 74% chance of being in one or the other class. Very, very simple. Alright, so this is the same thing with the addition rule. So I'll leave that to you. I'm just going to do the instructor cheat. And again, you're going to see different problems than me anyway. but you've seen me do the addition rules already. Okay, now the rest of it's on multiplication rules. Here's still that multiplication rule for independent events. So here, if you roll a fair die and then roll a second fair die, those two rolls should be independent, right? What you roll on the first die has no effect whatsoever on what you roll on the second die. These are independent rolls. What is the probability that you roll a 1, 2, or 3 on the first die? Well, that would be a half, right? 3 out of 6, a half. And so I'm doing, I see probability of A and B. I'm doing multiplication here, right? And's indication for multiplication, or is indication for addition. Roll a 5 on the second die. So 1, 2, or 3 on the first die, that's a half. Times 5 on the second die, that's 1 out of 6. What's 1 half times 1/6? That's 1/12. So I have a 1 out of 12 chance of rolling a 1, 2, or 3 on the first die, and at the same time 5 on the second die. And again, the only reason I could just multiply those was because those two events are independent. Right? Rolling one die, rolling a second die have nothing to do with one another. Right? The outcome of the first die has no effect on the outcome of the second. All right. Pardon me. All right, and this one, oh, okay, I'll go to the formula, right? This is, again, use the multiplication rule for independent events. So if A and B are independent events, with the probability of A being 90%, probability of A and B occurring at the same time is 54%, what would be the probability of B occurring on its own? All right, so again, going to a little piece of paper here, and just having the formula for you. Get rid of the calculator. I'll keep it up because there's some decimals here. All right, so we're told this, the probability that A and B occur at the same time is 0.54 equals, if they're independent events, it should be equal to this. They will be equal to this. The probability of A is 0.90, multiplied by the probability that B occurs, and we do not know the probability that B occurs. All right. So now again, I'm solving for probability B. Now this isn't going to involve addition or subtraction. This is going to involve division. Right? I would divide by 0.9 to get that to cancel and get the probability of B on its own. Same thing over here. Right, I would divide by 0.9. And in dividing these, probably should be able to do this in my head, but 0.54 divided by 0.9. So 0.6, 3/5. Okay. So we get the probability that B occurs on its own is 60%, 0.6. So that's what I enter here. Wonderful. All right, now there's one last objective that involves conditional probabilities. I've mentioned the conditional probability earlier. So let's see, it's use the multiplication rule for conditional probabilities. All right, so I'm going to show you the instruction on this. So let's see. So in this section, we'll talk about how to calculate the conditional probability of events. All right. So remember, that's the probability of one event given that another event has occurred. All right, and here it is. The probability of A given that B has occurred is calculated this way. The numerator, you have the probability that they both happen at the same time, divided by the denominator is the probability of the event that happened, the event after the bar, the event that has occurred. And if you multiply both sides by the probability of the event that has occurred, if you multiply both sides here by the probability of B, you get a rule that's similar to the one I showed you earlier. The probability of A and B is equal to the probability that A, let's say B happens, the probability of B times the probability of A given that B has happened. All right, so both of these formulas are equally valid, and I'll write them up as we go through problems. So here it is again. they have some examples. I just want to get some problems. I'll let you read the examples on your own when you look at the instruction. There's quite a few there. All right. Now some key terms at the bottom here. These are going to come up quite a bit. All right. The words with replacement and without replacement. When you see with replacement, right, when a population element can be selected more than one time. So after choosing an element, it is put back. It is put back in before the next one is taken. All right. So if I have a deck of cards, 52 cards, and I say I'm selecting them with replacement, that means when I pick a card, I look at it, I write it down, and then I put it back. So there are still 52 cards in the deck to pull from. Without replacement means I pull the card, I look at it, I write it down, and then I don't put it back. I set it aside. And then when I pull again, I have 51 cards. All right. So with replacement is I pull the object, record it, and put it back. So I have the same number of objects that I started with again. Without replacement is I pull the object, record it, and throw it away, and then I have one fewer to pull from on the next pull. So, a NPR Robert Wood Johnson Foundation / Harvard T.H. Chan School of Public Health poll, that's a mouthful, asked adults whether they participate in a sport. Given that the notice again the word given here, telling me that there's probably some sort of conditional probability going on. Given that the probability that a randomly chosen adult is a woman is 51%, and the probability that a randomly chosen adult is a woman and plays a sport is 0.08, 8%, what is the probability of an adult playing a sport given that the adult is a woman? All right, so I'm going to write down some letters here, a piece of paper. Get rid of the calculator. All right. So I'll go through these now. Let's have, I'm going to make up some letters instead of A and B all the time, because it's not always going to be A and B. Let's say W represents the event that the adult chosen is a woman. And we were told that the probability that a randomly chosen adult is a woman, so the probability of W is 0.51. Right? This was in the problem. The next part of that sentence is, and the probability that a randomly chosen adult is a woman and plays a sport is 8%. So let's say S is adult chosen plays a sport. Now they told us they said the probability that a randomly chosen adult is a woman and plays a sport. So as a woman and plays a sport. So W and S is 0.08. And they're asking us to calculate what is the probability of an adult playing a sport. So the probability of S given that adult is a woman. So that's the probability of S given W. Now if you replace these with A and B in the formula earlier, remember this is the probability of S and W, or W and S. Saying S and W, W and S is the same thing, divided by, so it's the probability, this is conditional probability. Conditional probability can be calculated this way. The numerator is the probability that both events happen at the same time, probability of S and W, divided by the probability of the event that happened, the event to the right of the bar, the probability of W. And we have these. Right? We have these. The probability that the adult is playing a sport and is a woman is 0.08 divided by, and then the probability that a randomly selected adult is a woman is 0.51. And they ask us to round to 2 decimal places. So I'll pull up the calculator here. So we got 0.08 divided by 0.51. And if I round that number there that you're seeing in the calculator to 2 decimal places, this is approximately 0.16, right? Because it's 156. The third one's 5 or higher, so I bumped the second one up to 0.16. So approximately a 16% chance that if I select a person at random and they're a woman already, and if I select a woman at random, the probability that they play a sport. And this is the probability that a person plays a sport given that they are a woman. Right? So basically this is saying what's the probability that a woman also plays a sport? Because I'm selecting from the group of women. All right. So back on the site here. So it's approximately 0.16 when rounded to 2 decimal places. Again, please read carefully. Look at how they want you to enter your answers. Okay. Now they called it M and W. I called it S and W. It doesn't matter. All right, so here, so we're given that the probability of B occurring given that A has occurred is 84%. The probability that A has occurred, right, the event that happened, the probability of that happening, A, is 43%. They're saying what's the probability of B and A occurring at the same time? So again, back to the paper here. So again, the probability we're given this, the B given A. All right, we're given that, and according to our little formula earlier, right, the probability of B given A, get rid of this, should be the probability that they both happen at the same time, so B and A or A and B, it doesn't matter, divided by the probability of the event that happened, the probability of A. And using this formula, we had this, the probability of B given A is given to be 0.84. We're trying to find this numerator. I don't know the probability of B and A occurring at the same time. Divided by, and we have the denominator over here, the probability of A is 0.43. And I just take this and do some algebra, right? Multiply both sides. I'm trying to get the probability of B and A alone. It's being divided by 0.43, so I multiply both sides by 0.43. All right, now I'll just punch that in. So I'll take 0.84 times 0.43. And we're asked to just provide your answer below, so no rounding. So 0.3612, a little over 36%. So we get the probability of B and A alone is, the product of these two is like 0.3612. And that's what I'll enter. 3612. Great. Alright, so I'll do one more of these and then probably just do a cheat on the last one and get it over with. But you see what's going on, hopefully, with this formula for conditional probability. So here, the probability that a product passes quality control inspections is 0.88. The probability that it passes quality control inspections and is packaged for shipment immediately is 0.03. What is the probability that it is packaged for shipment immediately given that it has passed quality control inspections? Right. So again, I'll just say, I'll just actually pull this up. Let's do this. Hopefully this isn't too small. All right. So they're asking us for what's the probability. Now they say, what is the probability that that it is packaged for shipment immediately? So I'll say S for shipment. Say S represents packaged for shipment immediately, given that it has passed quality control inspections. So I'll say Q represents past quality control inspections. Remember, according to our little how to calculate conditional probability, this should be equal to the probability of S and Q divided by the probability of Q, right? The event that happened in the denominator. Well, we are given both of these things, right? The first statement there, the probability, the first sentence is the probability that a product passes quality control inspections is 0.88. That's the probability of Q. That's the denominator here. So that's 0.88 in the denominator. The second sentence, the probability that it passes quality control inspections and is packaged for shipment immediately, that's this numerator, S and Q. You know, passes quality control inspections and is packaged for shipment immediately. It's 0.03. And we're just dividing these, and it says round to 3 decimal places, right? Round to 3 decimal places. All right, so now I'm going to actually do this. All right, we'll go here, pull the calculator up. It's already up, cool. And I'm doing 0.03, right, divided by 0.88. And to 3 decimal places, so that's approximately 0.034, and then there's a 0 after, so it would just stay 0.034. Alright, so back here, let's get rid of this, 0.034. Wonderful. Alright, and then I think there's one more I gotta do, and it's probably similar. Yeah, it's another one where you're just dividing some numbers because you're finding the probability of something given something else. You're finding another conditional probability, and then again round your answer to 3 decimal places. I'll just put the cheat in and submit, because again you're not going to see the same exact numbers, same exact problems that I am. And there's your formula there again. Okay, all right, I believe that's all. All right, so hopefully again watching this helps guide you through section 3.3's assignment when you do it on your own. Of course, do the reading in OpenStax, watch other videos that I've posted on Canvas from YouTube and all that, and take notes and practice extra problems in the reading in the OpenStax book. You know, get more and more exposure to the material. You know, the more you see it, the more you practice it, the more you do it, the better you'll get at it. It's just the way it is with most things. All right, so hopefully this is a good guide for you, and I hope you have fun when you're doing your own assignment for section 3.3. And thank you very much for watching.